Dear students, we will study unsymmetrical fault analysis, unit number 5 of PS2, our system 2. First, symmetrical components. This is transformation of symmetrical components. So we say voltages are balanced when voltage of phase A is equal to voltage of phase B is equal to voltage of phase C. So all three phases have equal voltage and phase displacement from one another is 120 degree. So this type of system is called balanced supply system. When VA is equal to VB is equal to VC and angle is 120 degree electrical from one another, then we say system voltage is balanced system voltage. Now positive phase sequence. Positive phase sequence. When positive phase sequence is ABC or RYB. In positive phase sequence, voltage VA, when voltage in positive phase sequence, voltage of phase B VB lag VA by 120 degree. Then VC lag VB by 120 degree, or we can say VC lag VA by 240 degree, or in another way we can say VC lead VA by 120 degree. So we can show this thing like this. If this is VA and this will be VB and this is VC. This is 120 degree, this is 120 and this is also 120. So in three phasors are expressed in terms of reference phases. Here VA is taken as a reference phasor. So VA is taken as a reference at an angle 0. So VB will be equal to alpha square VA. So this is 120 degree, nothing but alpha. This is from VA, this is 240, nothing but alpha square. So from this VC in terms of reference phasor, it will be alpha VA. The alpha is complex operator, like operator J. J is 120 degree. Similarly, alpha is defined as e raised to j 120 degree. So it has properties. Following properties. One is alpha square. Alpha is e raised to j 120. So alpha square is nothing but alpha into alpha. So alpha 120 e raised to j 120 e raised to j 120. This is e raised to alpha square is e raised to j 240. So this is nothing but conjugate of alpha. And second property, alpha square of conjugate, this is equal to alpha. Third property, alpha cube, if we simplify, alpha cube is equal to 1. And property 4 is alpha plus alpha square is equal to 0. These are the 4 properties. If we simplify this thing, alpha, this is alpha 240, alpha square is nothing but j 240, it is nothing but conjugate of alpha. Second property, alpha square conjugate is alpha. Third property, alpha cube is equal to 1. Fourth property, 1 plus alpha square is equal to 0. Suppose this is equation 1. Then phase sequence, if phase sequence is ACB or RBY, positive sequence is ABC or RYB. Now if phase sequence is ACB or RBY, then it is called negative phase sequence. Then it is negative phase sequence. Negative phase sequence. And in terms of alpha, we can write VA, this is reference phasor, VB is equal to alpha VA, and VC is equal to alpha square VA. The set of balanced phasor is fully characterized by its reference phasor VA, and its phase sequence will be either positive or negative phase sequence. Generally, suffix 1 is used to indicate positive sequence phasors. Suffix 1 used to indicate positive sequence phasors. So that we can write VA1, positive sequence of phase A V component VA1, then VB1, this is equal to alpha square VA1, and VC1, this is alpha VA1. This is equation 2. Same we can show, this is VA1, this is VB1, this is VC1. So this is VA1, VB1, VC1 positive sequence voltage phasors. So this is 120 degree. So VC1 we can write is equal to alpha VA1, and this is alpha square. So VB1 we can write as alpha square VA1 with respect to reference VA1. Suffix 2 used to indicate negative sequence phasors. So it's to use to indicate negative sequence phasor. And set of negative sequence phasors we can show like this. This is VA2 reference. This is VC2 and this is VB2. This is VB2, VC2. This is alpha 120 degree and this is alpha square 240 degree from reference phasor. So we can write equation. So set of negative sequence phasors. So the set of negative sequence voltage phasors. Negative sequence voltage phasors, like we can write VA2, this is reference, VB2 is alpha VA2 and VC2 is alpha square VA2. This is 3. So this is alpha and this is alpha square. Alpha square is 240, alpha is 120. This is equation 3. Now 3 voltages are equal in magnitude and having same set, having same phase, then it is called zero sequence phasors. Then three quantities of voltage, three voltages. This is 3 voltage phasors of equal magnitude, and having same phase, then it is called zero sequence phasors. It is zero sequence voltage phasors, and it can be written as, on vectorially we can show, this is VA0, voltages of same magnitude. So vector length of this should be same. This is VB0 and vector length of this is VC0. So all three vectors have same magnitude, equal magnitude and no phase displacement. These are the parallel. So these quantities are called this is called zero sequence phasors and can be written as VA0, VB0 is equal to VA0, VC0 is equal to VA0. So that we can write VA0 is equal to VB0 is equal to VC0, and this is equation number 4. So set of 3 voltages may be unbalanced and the voltages are expressed in terms of positive sequence component, negative sequence component and zero sequence component, and the same is expressed in symmetrical component. VA is equal to VA1 plus VA2 plus VA0. So positive sequence component, negative sequence component and zero sequence component. This is equation 5 for voltage VA. Similarly, voltage VB. VB is equal to VB1 plus VB2 plus VC VB0. So this is positive sequence, negative sequence and zero sequence component. This is 6. Similarly for VC, VC is VC1 positive sequence component, VC2 negative sequence component and plus VC0 is zero sequence component. This is equation 7. So that we have positive sequence phases, we have already seen positive sequence phases. So we have already seen positive sequence phases as VA1, this is VB1 lagging VA1 by 120 degree and this is VC1. These are the positive sequence phases. Then this is in terms of alpha, VC1 is alpha VA1 and VB1 is alpha square VA1. Similarly, negative phase sequence we can show like this. This is VA2, this is, as it is negative sequence component, this is VB2 and this is VC2. This is alpha 120 degree. So VB2 is equal to alpha VA2 and this is alpha square, this is 240. So VC2 is alpha square VA2 and zero sequence component we have seen all phasors of equal magnitude and same phase displacement, zero phase sequence, parallel VA0, VB0, this is VC0. This is the set of zero sequence component. So from this, from equation 5, we can write as in terms of alpha, we can write from 5. Equation 5, we can write VA is equal to VA1 plus VA2 plus VA0. Before going to this, we can find the resultant of all this. So first of all, vector VA1 is plotted. So this is vector VA1, then vector VB1 is plotted at 120 degree. This is VB1 and then VC1 is plotted. This is VC1. Now from this VA1 plus VA2 we have to determine VA. So VA1 plus VA2. So to this vector VA2, plotting VA2 here parallel to this VA2 and equal to VA2. So this is VA2 and then parallel to this. So VA1 is vertical plotted, VA2 is horizontally plotted, parallel lines, and VA0 is plotted parallel to this. So this is VA0 and sum of three components, this VA1 plus VA2 plus VA0, this is nothing but VA. Similarly, while finding VB, this is VB1, then VB2 is plotted parallel to this vector. So this is VB2 parallel to this and equal. This is VB2 and VB0 is plotted parallel to this vector. So this is VB0 and joined with this is vector VB. Similarly, we have VC1 this. VC2 is here. So from VC1 parallel to this vector, VC2 is plotted here. So this is VC2 and VC0 is here. From VC2, line parallel to VC0 is plotted. So this is VC0 and phasor sum of VC1, VC2 and VC0, this is nothing but VC. So these are the positive sequence, negative sequence and zero sequence component of corresponding phases. This is added to get phase voltage VA, VB and VC. So from this it is clear that vector length of VA is not equal to vector length of VB is not equal to vector length of VC. At the same time, angle between VA and VB not 120, VB and VC is not 120. So this you can see, these are the unbalanced voltages. These are the unbalanced voltages. Now writing equation for phase VA we have already written. So this is VA is equal to VA1 plus VA2 plus VA0 and this is equation 8. Similarly for phase B we can write VB is equal to VB1 plus VB2 plus VB0, this is equation 6 and putting alpha, so this is putting in terms of alpha, VB is equal to VB1 is alpha square VA1 plus VB2 is alpha VA2 and VB0 we have seen VB0 is equal to VA0. So this is equation 9. Similarly for equation for voltage VC, so we have equation 7, VC is equal to VC1 positive sequence component, VC2 negative sequence component and VC0 zero sequence component. So this is equation 7. But from this diagram we have seen VC1 is equal to alpha VA1, VC2 is equal to alpha square VA2 and VC0 is equal to VA0. So this is VC and this is equation 10, equation number 10. Now writing equation 8, 9 and 10 in matrix form. Equation 8, 9 and 10 in matrix form. So we can write VA, VB, VC. This is equal to 1, 1, 1. Alpha square, alpha 1, alpha, alpha square 1. And this is matrix of element VA1, VA2, VA0. This is equation 11. Above this equation 11 we can write, or VP is equal to AVS. This is equation 12. VP is a column matrix of where VP is equal to VA, VB, VC. This is vector of original phases. This is vector of original phases. VP is vectors of original phases, and VS is equal to VA1, VA2, VA0. This is called vectors of symmetrical component. Vector of symmetrical component. Symmetrical components are VA1, VA2, VA0. And matrix A is defined as, A is like this: alpha square, alpha 1, alpha, alpha square and 1. So this is equation 13. So we can write from this, we can write from equation 12, we can write VS is equal to A inverse into VP. This is equation 14. And same we can write, or first calculating, first finding the inverse of matrix A. So inverse of matrix A is of 10 and 1 upon 3 into, in matrix 1 alpha, alpha square, 1 alpha square, alpha 1, 1, 1. This is inverse of matrix A, and this is 15. Now from above we can write equation 14 as, equation 14 we can write as VS is VA1, VA2, VA0, and A inverse is 1 upon 3, then 1 alpha, alpha square, and second 1 alpha square, alpha, and third row 1, 1, 1, and VP is vector of original phases. This is VA, VB and VC. So from this we can write VA1 VA1, this is equal to 1 upon 3 VA plus alpha VB plus alpha square VC. Then VA2, this is equal to 1 upon 3 VA plus alpha square VB plus alpha VC. And VA0, 1 upon 3 is VA plus VB plus VC. So this is equation 16, equation 17, and this is equation 18. So from above symmetrical component, the symmetrical components from original voltage phasors can be determined. Now these equations for voltages can be applied for the currents as this is for currents. Same way we can apply the above equation for currents also. So for current we can write IP is equal to A into IS. This is equation 19, and IS is equal to A inverse of into IP. So this is equation 20, where IP is phasor of current phasor of original phasors. This is IP is IA, IB, IC, and IS is equal to symmetrical components IA1, IA2, IA0. So 19 we can write from equation 19. From equation 19 we can write IP as IA, IB, IC, and matrix A. Already we have seen 1 1 1, alpha square alpha 1, alpha alpha square 1. This is matrix of matrix A, and this is the matrix of symmetrical components IA1, IA2, IA0. Now from this we can write equation for IA. Therefore IA is equal to IA1 plus IA2 plus IA0, equation 21. Similarly for current IB, this is equal to IB1 from matrix IB is equal to alpha square IA1 plus alpha IA2 plus IA0. This is equation 22. And for current IC, this is alpha IA1 plus alpha square IA2 plus IA0. This is equation 23. Now from equation 20 we can find out the symmetrical components in terms of original phasors. So from 20, from equation 20, IS is IA1, IA2, IA0, and A inverse we have seen this is 1 upon 3 1 alpha square 1 alpha square, alpha 1 1 1, and this is IP, IA, IB, IC. So from this symmetrical components can be determined. So symmetrical component, positive sequence components, from above we can write IA1. IA1 is 1 upon 3 IA plus alpha IB plus alpha square IC. This is 24. And similarly IA2 is 1 upon 3 IA plus alpha square IB plus alpha IC. This is equation number 25, and zero sequence component is IA0 1 upon 3 into IA plus IB plus IC. This is equation 26. Now consider three-phase star connected system with neutral grounded. That neutral provide, consider three-phase system. Three-phase star connected system with neutral grounded. So neutral provides return path to the current. Now suppose this is the star connected three-phase system. This is neutral point N. Neutral is grounded. This is neutral point N. This is A, B, C. This is voltage, line voltage V, A, B. This is line voltage V, B, C, and this is line voltage V, C, A. These are the line voltages. Now current through phase A is IA, that of phase B IB, that of C is IC. These currents are entering in the neutral, and neutral is providing return path to the current, and this is the neutral current IN. This is VA, VC, this is VB. Now we know that the sum of three line voltages is equal to 0. Sum of three line voltages is equal to 0. Therefore, zero sequence components of line voltage is 0. So, zero sequence component of line voltages is 0. This is because the sum of three line voltages is equal to 0. Therefore, zero sequence component of line voltage is 0. So that we can write VAB0. This is equal to V1 upon 3 VAB plus VBC plus VCA, and the sum is 0. This is equation number 27. But sum of phase voltages may not be equal to 0. Therefore, zero sequence component VA0 exists, and therefore current Ia0 exists. So sum of phase voltages may not be equal to 0. Therefore, zero sequence component exists. Therefore, Va0 exists. And therefore, sum of three line current in the neutral this is Ia0 is 1 upon 3 Ia plus Ib plus Ic. This is 1 upon 3 Ia plus Ib plus Ic, and this is In. So 1 upon 3 into In. This is equation number 28. So neutral current is 3 times zero sequence current. Neutral current In is 3 times zero sequence current. But if neutral is absent, system is star connected, but neutral is absent, then there is no zero sequence current. So if neutral is absent, then Ia0 is In upon 3. This is 0. In the absence of neutral, zero sequence current not exist. So this is equation 29. Thank you.